This system of linear equations has a unique solution. We're going to find the solutions using Gaussian elimination and Gauss-Jordan elimination. First of all, we will start by writing the augmented matrix 1, 1, 6, 3, 1, 1, 3, 3, 1, 2, 4, -1. Now I'm going to multiply row 1 by -1 and add it to row 2 and put that into row 2. Multiply row 1 by -1, add it to row 3 and put it into row 3 in order to get zeros in column 1, rows 2 and 3. So we now have 1, 1, 6, 3, 0, 0, -3, 0, 0, 1, -2, -4. Next, I'm going to interchange rows 2 and 3. And that's going to give us the zeros in the bottom right triangle. So we'll have 1, 1, 6, 3, 0, 1, -2, -4, and 0, 0, -3, 0. Multiplying row 3 by -1/3 will give us the augmented matrix in row echelon form. 1, 1, 6, 3, 0, 1, -2, -4, 0, 0, 1, 0. And using back substitution, we will get that z equals 0, y minus 2z equals -4, which tells us y minus 0 equals -4, or y equals -4. And x plus y plus 6z equals 3 will tell us x minus 4 plus 0 equals 3, or x equals 7. So our solution is 7, -4, 0. Now, that's called Gaussian elimination. Alternately, we could have gone a couple steps forward, further, and made these three numbers into zeros, and that would have been the Gauss-Jordan method, because then we would have had row reduced echelon form, and the last column would have ended up to be 7, -4, 0. I'm going to use the Gauss-Jordan method in the next example. And so going down to the second example, we start with the augmented matrix 1, 1, 1, 4, -1, 2, 3, 17, 2, -1, 0, -7. So I'm going to take row 1, add it to row 2, put it into row 2, and -2 times row 1 plus row 3, and put it into row 3. That's going to give us 1, 1, 1, 4, 0, 3, 4, 21, 0, -3, -2, and -8 plus -7 is -15. Now I'm going to go ahead and add row 2 to row 3 and put that into row 3. Again, building the zeros in the bottom left-hand corner. So 1, 1, 1, 4, 0, 3, 4, 21, 0, 0, 2, 6. Now if I multiply row 3 by 1/2, I'll get a 1 in the third row, third column. I've left row 2 alone for the time being. I will get a 1 in position 2, 2 before we're finished, but I don't want to multiply by 1/3 yet in row 2 because that's going to introduce a fraction. So now I'm going to work toward getting these numbers to be 0. And it's the 1 and the 4 in column 3 that I'll eliminate first. So now row 3 is our operator. -1 times row 3 added to row 1 into row 1. And -4 times row 3 added to row 2 into row 2. So we have 1, 1, 0, 1 for the first row. We have 0, 3, 0, and 21 minus 12 would be 9, and 0, 0, 1, 3. Now I'm going to take 1/3 times row 2, put that into row 2, and this will give me 1s on the diagonal now. And I have one more 0 to obtain in row 1, column 2, and I'll get that by taking row 2 times -1. Add that to row 1 and put that into row 1. So I'm going to get 1, 0, 0, -2, 0, 1, 0, 3, and 0, 0, 1, 3. This is now in reduced row echelon form because we have the zeros in this triangle at the top as well as zeros in the bottom triangle and ones on the diagonal. From that we can read the solution: z equals 3, y equals 3, and x equals -2. So -2, 3, 3 is the unique solution to this system. And you can check that by substituting those values in for the variables in the three equations. All the three should be satisfied, and therefore the system is solved.